So now we move into chapter 5. The title of chapter 5 is Equilibrium of a Rigid Body. I encourage you, when you start in a chapter, reread the title a few times, maybe take a look at the major points that you can glean from the table of contents or the outline. You're going to look at section 5.1. It's conditions for rigid body equilibrium. Then you're going to do section 5.2, free body diagrams. Then section 5.3, equations of equilibrium. Then 2 and 3 force members, free body diagrams, equations of equilibrium, constraints, and statical determinacy. Yeah, that's exactly it. The key topic isn't hidden in this chapter from you. And it's free body diagrams, and it's very rare. I mean, they didn't even say 2D free body diagrams and 3D free body diagrams. They just said free body diagrams. So they actually, exact wording is repeated for a section. So these sections have the same exact wording. Oh yeah, equations of equilibrium. Yeah, 2D, that's a good point too. They should have that's repeated as well. So this is really the key idea, free body diagram. All right, there's another word. If the body is rigid, what does that mean? Does that mean that it's cold? Does it mean that it's long and slender, short, stubby, will not deform when subjected to loads, or will return to the original shape after the loads are removed? D? Yeah. So sometimes we see words, we get a little confused. And so rigid means it's not going to deform, even though I load it. It has negligible deformation. When you move into solid mechanics, you're going to do a lot of linear elastic material analysis before you move on. And in the linear elastic, you'll actually calculate the small deformations. And often they'll approximate the small deformations. You calculate them, but you don't really update the system. The dimensions and the shape of it are unchanged, because the deformations are so small. In solids, when you unload it, the structure of the object goes back to its original. If it's linear in elastic, you didn't overload it. Okay, next question. If the body is in equilibrium, it is at rest or is moving with unchanging speed? Is moving with unchanging speed or is at rest? Hey, yeah. And so a lot of systems, you actually have a system that's actually moving. But if it's moving without accelerating, it's in static equilibrium. So basically, most of the time we think, oh, that has to be at rest. But no, it can be at a constant speed. All right. So what are the conditions for the rigid body equilibrium? Well, sum of all the forces acting on the body must equal to 0. So this is sum of the forces equal to 0. That's a vector equation. And we'll have 2D, we'll have two linear equations, scalar equations. Sum of the forces in the x equal to 0, the sum of the forces in the y equal to 0. And when we move to 3D, sum of the forces in the z equal to 0. Okay, what about the sum of the moments? Now, so not only do we have sum of the forces, we have the sum of the moments. And you have some of the moments that are from all of the forces. You could have multiple forces, hence each of those forces could induce a moment. And then you could also have what they call couple moments. What are those? Free vectors, free moments. And so the combination of moments due to forces and couple moments, that has to equal to 0. So we have a sum of the moments. Maybe we say about the point, the origin, that's convenient, is equal to 0. That's a vector equation. Maybe I should put the vector notation on top of that 0 to emphasize this is a vector notation equation. And then we're going to have the sum of the moments around the x-axis, sum of the moments around the y-axis, and the sum of the moments around the z-axis. And those are our three scalar equations. Now, when you work in 2D, just like up here, we said, okay, 2D, we're going to have the sum of the forces in the x and the sum of the forces in the y must equal to 0. We only have one moment equation in 2D. That would be the sum of the moments about the z coming perpendicular to the xy. It's out the z-axis. So that's the 2D. But when you move into 3D, you have not only 3 scalar force equations, you have 3 scalar moment equations. We will just solve 2D today. So one thing, we've talked about the free body diagram in the previous chapter, and it really was a free point diagram because our bodies were particles and they basically were points. So, but the idea was we already been introduced to this free. What do you mean free? Cutting it free from the surroundings, isolating it from the surroundings. That's what the notion of free is. And then on this diagram, you have to put all of your loads, all of the forces and all the reactions and any couples that are applied to the system as well. So any applied forces, if they have weights, they have to be there. And then the supports, when you cut it free from the surroundings, you have to replace those supports by the reactions. And then all couples. We'll solve some problems. The supports are a little tricky. So somebody says we have a roller. What is a roller? Oh, we have a pin or a hinge. What is that? We have a fixed support. Blah, blah, blah. More and more. So a roller would be something like this. So here is the rest of the world. And then the roller is between that and maybe my beam. My beam is the focus of the study. And what I would do is I'd come in and I would try to cut like that. And now I've cut through that roller and I have to replace the effect of the surroundings on my beam. And it would be something like, well, it's going to result in a force pushing up. F is pushing up on that bottom of my beam. So this is the roller. This is how you replace that support of the roller on my free body diagram being the beam. Here is two views of a pin hinge. So the pinned hinge is right here. Looking at it that way, that's the pin going in. You're looking down the axis of the beam. This is the beam that way. I'm going to cut through the pin, okay, and replace it such that I just have my beam, and then right there at the pin, I'm going to have some supporting reactions due to the pin and connected to the rest of the surroundings. And it's not that hard. Basically, you could have, this is the least common, this is the most common way of writing it. You would say, I'm going to have a supporting force, F in the X. So let's say the beam, if the pin broke, would want to move in that direction. Then you can see, oh, there would be a push because of the pin support, assuming it's still intact, hasn't broke, on the beam in the positive F of X direction. And then likewise, F of Y. This is the most common. And then if somebody said, well, I just want one magnitude of a force at an orientation, that's least common. You can do it that way as well, but there's two unknowns, just like there's two unknowns modeling the pinned hinge. All right, there's more of these. So you say, what about a fixed support? Well, let's say I have something rigid and it's either bolted, attached, or embedded inside. That beam protrudes out. Well, it's very rigidly supported or fixed support right there. Well, this is, you could have, when you cut it free from the surroundings, you'll have possibly a non-zero F of X, possibly a non-zero F of Y, and a moment to support that beam at that location. The way they've shown it being in this clockwise direction. In 2D, you could also show it in the counterclockwise direction for the moment. If I was drawing this, I would have probably shown it in the other direction. But when you have a free body diagram, what you're going to find is when you put your directions of your forces on it, that's important, because somebody else could assume it's in opposite direction and their answer will be the negative of yours. So somebody could compute, oh, it's 50 newtons. Somebody else say, no, it's negative 50 newtons. You go and look at each free body diagram, and they could be consistent, both correct. Well, there's a long table. I don't have time to go through it. You need to go through it because it's really how these supports are replaced by reactions that affect our object. So here's a cable, just like a rope or a chain. And that cable can only be in tension. You can't push a rope. So if it's attached to my object up here, I want to cut that object free, it would have a force in the direction of that cable. Likewise, a link can be in tension or compression. No buckling. Next class, solid mechanics, you can buckle long, slender objects in compression. But if it's in tension, won't it, when you cut like this, won't it be in pulling? Or if it's in compression, and the table goes on. So now what we want to do is get those equations of equilibrium for 2D, some of the forces in X, some of the forces in Y, some of the moments about the Z-axis coming out perpendicular. Let's solve this problem. The steel frame is loaded with a force and couple moment. Well, we need to find our couple moment. There it is. It's 30 kilonewton per meter. It looks like it's applied to the end of the top member of this steel frame. Okay, now where's our force? 70 kilonewton. So one force and one couple moment. All right, it's supported by a pin at A. So here's our reaction or support. It's pinned at A. The way to understand that pin, let's say I didn't have this cable, this whole frame could rotate and fall down either to the right around that pin, rotating around pin A, or fall down, rotating to the left. If somehow the frame wants to move downward into the foundation, that pin's going to say, nope, I'm going to have a reaction. It'll have a net positive push back up. Likewise, if something in the frame said, I want the whole frame to move to the left, the pin will have a reaction and it'll have a pushback in the positive X direction. So there you go. Hopefully the pin reaction is pin support. It makes sense. All right. And it also has a cable from point B to C, and they give the similar triangle so we know the orientation of that cable. Can that cable be in compression or can it only be in tension? Cables can only be in tension. All right. Determine the horizontal and vertical components of the reaction at pin A. They're asking for two things, the horizontal and vertical components of reaction at pin A. You could introduce notation. You could say, look, I'm going to be looking for the force in the X at pin A and the force in the Y at pin A. Or a lot of times the book will just use, and a lot of people, myself included, will just say AX. It's just the magnitude of the force in the X component, and then this would be similarly AY. I like both of them. It's just that the shorter notation is often helpful, as you have to rewrite and rewrite your equations. And then also solve for the tension in the cable B to C. So what's the approach to a problem like this? Clearly understand what we're trying to solve for. Three things. The horizontal reaction at pin A, the vertical reaction, and then the tension. Those are our three things. We introduce some notation for the three unknowns that we're trying to solve for. Then we decide on an object of study, a free body diagram. This is pretty easy to do. You come in and you cut that cable. You come down. You cut through air, which has no interaction with the object. You cut through the pin support. You come up. You include both the load and the couple moment. Or if you wanted to, there's a little, you could cut like right in here, and okay, the couple moments applied to the object, but just it's It's part of the system. The load and the couple moment are part of the system. So when you do this, maybe if somebody said, put your free body diagram in this box for this problem, you would be forced to re-sketch as best as you can do it. You would have a tension force, tension B to C, and maybe you even move that little similar triangle up so it's a 3, 4, 5 orientation. You then come down here and you would have maybe A in the X and A in the Y. They're applied at point A. Sometimes we have some insight. Oh, I think the pin is going to have to pull down on my frame, or the pin is going to have to push up on my frame to keep it in equilibrium. Sometimes you don't have that insight, so just pick the traditional positive X direction, positive Y direction for both of those. And if you get a negative answer, then hey, if you did the math right, then it's actually acting in the opposite direction. Okay, don't forget our 30 kilonewton meter couple moment, and then don't forget our load of 70 kilonewton. I find, especially when you move to 3D, it's very helpful to try and reuse our illustration given to us in the problem statement. Because right now what I need to do is I need to copy down all those dimensions as well. In the interest of time and space, I'm not going to copy down those dimensions. But there's a free body diagram. You would need to put in your dimensions, 2 meters here, 6 meters here, etc. Okay, so let's do this. You're going to have 3 possible equations. Sum of the forces in the x must equal to 0. That'll give me a linear algebraic equation. Let's just do that one first. Okay, so ace of x is 100% in the positive x direction. Okay. That 70 kilonewtons is down. The couple moment doesn't do anything in the x. And I have negative 3/5 of the tension in the cable B to C. Those are my two. One is in the positive x, one's in the negative. They sum. Do you agree with that? They look good? Okay. I have 2 unknowns with 1 equation. I need to keep going. So I'll get another equation. I'll say the sum of the forces in the y equal to 0. Okay, let's write that equation. So what do we have? We have AY moving upward, push in the positive y direction. We have negative 4/5 of the tension B to C, that's down. And we have 70 kilonewtons in the down, so I need to put a negative sign in front of that. And that's it. That sums to 0. Look good? Now I have unknown, unknown, unknowns. 2 equations, 3 unknowns. Need another equation. Okay, at this point, you have some choices. You could do the sum of the moments about any point. Sum of the moments, any point on the object, that's easiest. Or even off of the object. That's a little more complicated. Let's not worry about that right now. But conceptually, you can go for sum of the moments on any point, even off of the object. Okay, but the most logical would be A. If you do the sum of the moments about point A, we'll come back and say, why did you pick point A? Okay, but let's do it. So if I do the sum of the moments about point A, does ace of x induce a moment about point A? No, that's one of the reasons. What's the second reason? Does ace of y induce a moment about point A? No, that's the second. Those are the 2 reasons why we picked point A, is a logical choice. It takes a little insight. You need to solve a lot of problems to see that. But A is a great choice. Okay, so let's do it this way. We're going to have the 30 kilonewton meter in the, I'm going to do this. This is the clockwise direction. Okay, so everything I'm going to do is going to put the clockwise and the positive. It could be counterclockwise would be positive. Then I'd have to put a negative 70 or negative 30 kilonewton meter there. Okay, then we're going to have plus the 70 kilonewton with its moment arm. What's its moment arm distance about point A? 2 meter, isn't it? And it's in the clockwise as well. So that's we just, for this problem, picked clockwise to be positive. All right. Now, what about this tension B to C? You could do it in 2 ways at least. You can decompose it into 2 parts. One would be the tension B to C, and I would pick off the 3/5, right? That's the horizontal component. And that 3/5 horizontal component has a moment arm distance of, you tell me, if I pick off the horizontal component, the 3/5 of the tension B to C, what's the moment arm distance? 6, exactly, 6 meters. Then I have to revisit the direction. So it doesn't make it want to rotate in the negative, the negative sense, because we put positive is clockwise. And then I need to continue this equation, so it'll be the tension B to C, and now our downward component, I know I'm exaggerating their lengths, and what's its moment, first of all I have to pick off the component, isn't it 4/5 downward? Okay. And then what is its moment arm distance? 2 meters. And does it make it want to rotate in a positive, negative sense, right? Negative. So they have to sum to 0. We pause. We triple check our work. I wait for a few thumbs up if you agree. 1, thank you. 2, thank you. 3, thank you, thank you, thank you. 4, 5, 6, thank you. 7, thank you. 8, good, thank you. 9, thank you. 10, perfect. All right, so we're good to go. Now at this point, we do have 3 equations with 3 unknowns, and we can solve them. And some experience solving these equations, because we picked point A for the sum of the moments, 2 of the unknowns aren't in that moment equation. There's only 1 unknown, and it's only tension in B to C. So what I'm going to do is I'm going to pause. I'm going to let you solve for the tension B to C. And after I get a few of those, I'm going to move on. All right, so we end up showing that the tension in the cable is 32.7. Then we take that answer, put back into our equation, can solve for a sub y, and then put it back into the first equation, can solve for a sub x, and those are the values of a sub x and a sub y. All right? Okay. This chapter is just solving a lot of problems because you mastered sum of forces and description of forces and 2 and 3D, and you've mastered all the moment calculations. That was a big thrust of the previous chapter. There. All right. The member is pinned at A, so we find our member, and there's the pin at A right there, and has a smooth slot with fixed peg B. This is hard to see, but the opening is the slot in our member, and the peg is this blue dot sitting inside that slot. And that peg is rigidly attached to the universe, to the surroundings. Okay, so if this reddish member wanted to move this way or that way, it could. The peg at B would let it slide within the slot. But if it wanted to move this way or that way, it would say no. It would develop a reaction, a force would be exerted onto that reddish member that has the slot in it because of the peg. All right. So this one is described in this table. So when you're introduced to a new support, you go look in that table and then read about it and come up to speed. All right. And it has a cable attached at C. And this cable, as shown to be in tension with a magnitude of 800 newtons at an orientation of 20 degrees down from the horizontal. This red member that's pinned at A is oriented 30 degrees up from the horizontal. So we're given some orientation. The question is, determine the horizontal and vertical components of the reaction at pin A. So what are the two unknowns that you would like to solve for? And what symbols would you like to use for those two unknowns? I'm going to pause, walk around, and see what you come up with. So we're going to introduce the notation AX and AY. Those are the two horizontal and vertical supports at pin A. We go ahead and cut this member free from the surroundings. That cut for the support, that pin, that B, is really hard to do, but you would cut through this cable and then come up. Your free body diagram would look like something like this, and you would have A sub X and A sub Y. And then here, I would say, let's call it B. We know the orientation of B, we just don't know the magnitude. There's not BX and BY. It's B only perpendicular to that slot, not tangential, nothing tangential to the slot. So that's B. And if you look at it, this has to be perpendicular to the member because the slot is aligned with the member. All right. And then we come out here and we have, this is 800 Newton. And we could put in our 20 degree orientation and our 30 degree orientation. Let me move the location of the magnitude B. Okay. A little geometry here. If I go perfectly up and down, that's a vertical, right? Can somebody deduce what this angle is right here? What's this angle right here? Is it 60 degrees, 45 degrees, 70 degrees, 30 degrees, 20 degrees? 30. How did you get that it was 30? There's a lot of ways to do it. Let me describe one way that I do it conceptually. Is if I took that member and I sort of kept moving it downward, 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 and I laid it flat on the ground, okay? Then this angle for the direction of B and the vertical would be coincident. The angle would be 0, wouldn't it? If this is my angle theta right here, if the beam was consistently moved downward so then it became horizontal, that angle would shrink from 30 all the way down to 0. True? That's one way I like to think about it. Well, you could see that as this angle is being reduced, going from 30 down to 0, that angle's doing the same. All right, maybe you don't like that one. There's plenty of right triangles to pick from, aren't there? Yeah.
Would it be, could you just reorient the origin so that the x-axis lines up with the beam? Would that be acceptable for this problem?
Yes, you could. That's probably a little more sophisticated than I want us to do right now. But yes, change the x-axis to go like this. Well, you could, but let's do that, or let's solve it one way this way and then come back and then you could resolve it a different way. But you do have to get that this is 30-degree angle. Okay. And then let's leave the traditional x and traditional y coordinate direction on this problem. Okay. So now this is a good free body diagram. I have a force, and a force. Hey, they didn't ask me to solve for B, did they? But it's still an unknown, and I may have to solve for it. Okay, so let's do this. You can do the traditional sum of the forces in x equal to 0, what does it give you? The sum of the forces in the y equal to 0, what does it give you in the equations? And then the sum of the moments about a particular point. You can get more sophisticated, but this is the easiest to start off with. So let's do this. If I said the sum of the moments around point A must equal to 0, I'm going to get an equation. AX and AY will not be in that equation, but the unknown B will be, and then I'm going to get B. And I'm going to need B. I could tell I'm going to need B. Okay, let's do that. So, what is the sum of the moments around point A equal to 0? So, does B induce a moment about point A? Yeah. What is its moment arm distance? 70.7 meter or 70 centimeters, isn't it? Yeah. Yeah. This one's easy because that's your moment arm distance coming out. All right. And then that's going to make it want to rotate in the, I'm going to do this one. This will be positive. The counterclockwise will be positive for this problem. All right. So that'll be positive. And then how about this 800 newtons out here? Yeah. And here, depending on how you want to do it, if you wanted to, you could do this. If I go straight out right here, what is that angle? 30. All right. Sum of 30 plus 20 is 50. 30 and 20 is 50. If I come out here, what is this angle? This is now perpendicular. Do you see what I'm doing? I'm kind of like, okay, I got three angles that sum to 90. 20 was given. 30 I deduced. What's the other angle? This angle right here. 40. 40 degrees. Okay. Now, I look at it and I think if I take this 800 Newton, I can decompose it into something that's a line that's going to have an axis that'll go straight through point A, as well as a component that is perpendicular, which then has a moment arm distance of 70 centimeters plus 70 centimeters, 1.4 meter. So what is this magnitude? Think of this as a right triangle. Isn't this magnitude right here the 800 Newton times cosine of my 40 degrees? Did I do that okay? Okay, so that basically I'm going to have, and that's going to make it want to rotate in the negative sense, in the clockwise. So it'll be negative 800 Newton times the cosine of 40 degrees times a perpendicular distance of 1.4 meter. I'll put a 0.7 there to emphasize that, 0.7 meter and 1.4 meter. And they have to sum to 0. So I could rewrite, I say B is equal to 800 Newton times the cosine of 40 times 1.4 divided by 0.7, I'll just say 2 in units of Newton. I could run on that calculator, I could just use that equation later in the calculations. All right. Thumbs up if you followed that. Very good. Okay. Now we're really ready to do some of the forces in the x equal to 0. And again, I agree, you could probably do a sloped x, but let's just stay with our traditional x. Okay. So we're going to have a sub x. In the positive x, we'll have negative b times, what is that going to be? You're going to pick off the sine of 30. True? Because I dropped this back, that's a 90-degree angle. Okay, well, this is a bad-looking 30 degrees. Okay. And then we come out here, and now I want to decompose the 800 kilonewton into the, so maybe I look at, I'm going to exaggerate this triangle, that right triangle. And 800 Newton is the hypotenuse, and so it'll be plus 800 Newton times cosine of 20, that's 20, isn't it? Cosine of 20 degrees equal to 0. Did we do the sum of the forces in the x correctly? Since we did solve for b already, we can now solve for a sub x. A sub x comes in at 0. I would like some people to verify that, or maybe we can do it by equation. So a sub x is equal to b. b is 800 cosine of 40 times 2 times the sine of 30 plus 800 cosine of 20. This is minus. When you start to draw the free body diagrams, just please make sure that you draw it cleanly, especially the first time that you do it. Don't miss any forces, either they're applied or reactions or weight or body forces, and any couple moments. And then the supports, you just need to solve a lot of problems with different supports, and you'll get better at it. Thank you for your attention.